We all think we know what math is. It's that thing you did in high school with the graphing calculators and the messy chalkboards. It's a tool, a hammer we built to crack the nut of reality. We assume that the universe is out there doing its thing, planets orbiting, apples falling, light waving, and math is just the ledger we use to keep track of it. We think of it like a language, a way for us to describe what's happening, like English or French, but with more Greek letters and fewer adjectives. But wait, that's where the trouble starts. Because if math is just a human invention, a convenient shorthand we cooked up to describe the world, why does it work so unnervingly well? Why does a squiggle on a piece of paper in a basement in Princeton tell us exactly how a star on the other side of the galaxy is going to behave? Think about it. When an engineer builds a bridge, they don't just guess and hope the steel holds. They use equations, and those equations aren't suggestions, they are mandates. Richard Feynman, the legendary physicist who could see through the veneer of things better than almost anyone, once pointed out something deeply unsettling. He argued that math isn't just a tool for physics. It's not like a shovel you use to dig up the truth. It's something much more intimate. He suggested that you cannot truly understand the beauty, the actual character, of the physical world without a deep appreciation for the mathematical laws that govern it. Here's the thing, most people believe that if you just explained physics simply enough, you could get rid of the math entirely. You've seen the documentaries. They use analogies about rubber sheets and bowling balls to explain gravity. But Feynman would tell you that those analogies are actually lying to you. They are shadows of the truth. To Feynman, the math is the reality. And if you don't speak that language, you're looking at a masterpiece through a thick, muddy fog. Today, I want to show you why the relationship between math and physics isn't a marriage of convenience. It's a fundamental identity. We're going to look at why the universe seems to be written in code, and why that code is the only way we can ever truly touch the face of reality. To understand how we got to this realization, we have to go back, way back, to a time when people thought math and the world were two completely different kingdoms. For the longest time, math was about perfection, circles that were perfectly round, infinitely thin lines. The real world, meanwhile, was messy. It was full of lumpy rocks and wobbly orbits. Then came Johannes Kepler. In the early 1600s, Kepler was obsessed with the motion of Mars. He had years of data from Tycho Brahe, meticulous, agonizingly detailed measurements of where Mars was in the sky every single night. At the time, everyone believed planets moved in perfect circles because, well, circles are divine. But the numbers didn't fit. Mars was off just by a tiny bit, about 8 minutes of arc. Most people would have ignored it, but Kepler didn't. He spent years, trying to force those numbers into a circle. He failed. Finally, he tried a different shape, an ellipse. And suddenly, the math clicked. The messy, lumpy world of the heavens fit perfectly into a geometric formula. R equals backslash frac P1 plus backslash epsilon backslash cos backslash theta dollar. This was the first major crack in the wall. It was the first time we realized that the messy universe was actually following a strict mathematical script. But then came the giant, Isaac Newton. Newton didn't just find a shape, he found a rule. He realized that the reason the moon stays in the sky and the reason an apple falls to the earth are the exact same reason. He described it with a single, elegant equation, F equals G frac M, M2R $2. Think about that. He took the entire universe, everything from a grain of sand to the furthest star, and condensed its behavior into a relationship between mass and distance. Now here is where it gets strange. Newton didn't know what gravity was, he didn't know how it worked, he just knew the math. He famously said, hypotheses non fingo, I frame no hypotheses. He was saying, I don't know the why, I just have the how in the form of an equation. And for 200 years that was enough. The math was so powerful that it allowed us to predict the existence of planets we couldn't even see. When astronomers noticed Uranus wasn't moving quite right, they didn't look for ghosts. They used Newton's math to calculate where another planet had to be. They pointed their telescopes and there was Neptune, exactly where the math said it would be. Wait, let me say that differently. It's not just that the math helped us find Neptune, it's that the math knew Neptune was there before we did. The symbols on the paper had more information about reality than our own eyes did. This is what Feynman was getting at. Math isn't just a way of summarizing what we've seen, it's a way of discovering what we haven't seen. By the time we get to the 19th century, James Clerk Maxwell does the same thing with electricity and magnetism. He writes down 4 beautiful equations, but when he looks at them, he notices a symmetry, a mathematical gap. He adds a term to the equations just to make the math look more elegant, more consistent. When he calculates the consequences of that extra term, he discovers something staggering: electromagnetic waves. He calculates their speed, and it turns out to be $3 times 10 $8 meters per second. The speed of light. Maxwell didn't set out to explain light. He was just playing with the math of magnets and wires. But the math led him to the secret of light itself. It's like picking up a thread on a sweater and realizing the thread is connected to a tapestry that covers the whole world. This historical progression shows us that math isn't just a description. It's a map that is somehow more accurate than the territory itself. So why? Why does this happen? This is the deep dive, and this is where Feynman's insight becomes essential. Feynman argued that math allows us to see patterns that are invisible to the naked human mind. We are evolved to understand pushing and pulling. We understand fast and slow. But we are not evolved to understand the inverse square law or the divergence of a vector field. Let's try a thought experiment. Imagine you're trying to describe a character in a book. You can say he's tall and kind. That's a description. But in physics, math isn't like an adjective. It's more like the DNA. If you have the DNA, you don't just know he's tall. You know his blood type, the color of his eyes, and how he'll react to a specific virus 10 years from now. Think about the concept of conservation of energy. We're taught in school that energy cannot be created or destroyed. It just changes form. Sounds simple, right? A ball rolls down a hill and potential becomes kinetic, but that's just a story we tell. The reality is a mathematical symmetry discovered by Emmy Noether. She proved that the reason energy is conserved is that the laws of physics don't change depending on when you do the experiment. If I drop a ball today, it will fall the same way it will tomorrow. That time translation symmetry mathematically forces energy to be conserved. It's not a choice the universe makes. It's a mathematical necessity. Here's the aha moment. The physical thing energy is just a consequence of a mathematical property symmetry. The math is the why behind the what. Let's look at another example. This one is a bit more mind-bending: quantum mechanics. This is where Feynman really lived. In the quantum world, things don't have positions, they don't have paths. An electron isn't a little ball zipping around. It's a wave function, a cloud of probabilities described by the Schrödinger equation. Now ask, okay, but what is the electron really doing when we aren't looking? Feynman's answer was famously blunt: shut up and calculate. He wasn't being rude, he was making a profound philosophical point. He was saying that the question, what is it really doing, assumes there is a non-mathematical reality that makes sense to our human brains, but there isn't. The reality is the wave function. The math isn't a veil over the truth, it's the only truth we have access to. Let me show you what I mean. Think about the path integral formulation, one of Feynman's greatest contributions. He suggested that when a particle moves from point A to point B, it doesn't just take one path, it takes every possible path simultaneously. Through the center of the Earth, out to the moon and back, spinning in circles, it takes them all. You might say, that's ridiculous, that's not what happens. And you'd be right based on your common sense. But when you do the math, when you sum up all those infinite paths, the wrong paths all cancel each other out through mathematical interference. Only the right path remains. The path that follows Newton's laws is just the mathematical residue of infinite possibilities. What we see as a simple straight line is actually the result of a complex mathematical chorus. Let's pause, recalculate. If what I'm saying is true, then we have to confront a very weird possibility. Maybe the universe is math. This is an idea explored by physicists like Max Tegmark, but Feynman approached it more practically. He noted that there is a strangeness to the fact that the more we learn about the universe, the more mathematical it becomes. Look at the Standard Model of particle physics. It's the most successful theory in human history. It describes every particle and force we know except gravity, and it's built entirely on group theory, a branch of math that deals with abstract symmetries. We didn't find the quark because we saw it in a microscope. We found it because the math had a hole in it. We had a group of 8 particles, but the math suggested there should be 10, so we went looking for the other 2, and we found them. Think about how insane that is. Imagine you have a deck of cards and you notice that the 7 of hearts is missing. You don't just assume it's lost. You use the rules of cards to deduce that the 7 of hearts must exist somewhere in the universe, and then you go out and find it in a sealed room 3 miles away. That is what physics does with math every single day. But wait. Here is where it gets even more beautiful. Feynman pointed out that math allows us to see the connections between things that seem totally unrelated. This is the 3-for-2 storytelling I mentioned. Take the inverse square law. It's why gravity gets weaker as you move away, 1/R2. It's also why light gets dimmer as you move away, 1/R2. It's also why the electric force between 2 charges gets weaker, 1/R2. Why? Is it a coincidence? No, it's a mathematical consequence of living in a 3-dimensional space. If you spray paint from a single point, the area it covers grows with the square of the distance. The physics of gravity and the physics of spray paint are the same math of geometry. One insight, the geometry of a sphere, explains 3 completely different phenomena. Math is the connective tissue of the cosmos. So what does this mean for us? Why does it matter that the universe is written in this strange, abstract language? It matters because it changes our place in the story. If math is just a tool we invented, then we are the masters of it. We are the architects. But if math is the fundamental language of reality, then we are more like translators. We are trying to listen to a conversation that was happening long before we got here, and will keep happening long after we're gone. Here's the implication. If the relationship between math and physics is as deep as Feynman believed, then there is a limit to what human intuition can do. Our brains were built to survive on the African savanna. We were built to throw spears and find berries. We were not built to understand the curvature of spacetime or the probability amplitudes of an electron. This is why physics becomes so difficult for people. It's not because the concepts are hard in a traditional sense. It's because the concepts are non-human. They don't fit into our story-based way of thinking. You can't tell a story about a 4-dimensional tensor. You can only do the math, and this realization requires a certain kind of humility. It means admitting that the universe doesn't owe us an explanation that makes sense to our common sense, but that's also the beauty of it. Math is our exoskeleton for the mind. It allows us to reach into realms where our intuition fails. It's like a blind man using a cane to see the shape of a room. The math is our cane. It lets us feel the shape of the Big Bang. It lets us touch the event horizon of a black hole. It lets us predict the behavior of atoms we can never see. Think about the discovery of gravitational waves. Einstein's math, written in 1915, predicted that when 2 black holes collide, they should ripple the fabric of space itself. For 100 years, this was just a math thing. It was a squiggle on a chalkboard. People thought it might be too small ever to measure. But in 2015, we built LIGO, 2 massive laser interferometers, and we heard it, a chirp, a vibration in the math that became a vibration in our machines. The math had been waiting for us for a century. It was there in the equations, patient and true, until we finally built an ear sensitive enough to hear what the math was already saying. That is the power of the relationship Feynman described. The math isn't just part of the physics, it is the prophetic core of it. As we close this out, think about what this means for the future. We are currently staring at some of the biggest math gaps in history. We have general relativity, the math of the big, and quantum mechanics, the math of the small, and they don't like each other. The math breaks down when you try to combine them. To a Feynman-esque thinker, this isn't just a problem, it's a clue. It means there is a deeper math, a more elegant group that we haven't found yet. We are looking for the seven of hearts of the entire universe. And here is the avalanche I promised you. Every time we find a new mathematical relationship, it doesn't just answer one question. It unlocks 1,000 new ones. When Newton found his law of gravity, he didn't finish physics, he started it. He gave us the language to ask about orbits, which led us to ask about the speed of light, which led us to ask about the nature of time, which led us to the Big Bang. Each discovery is a pebble that starts a slide. The slide becomes a flow. The flow becomes an avalanche. We are currently caught in that avalanche of understanding. We are learning that the tools we thought we were using, these little equations and variables, are actually the very fabric of the world we're trying to measure. Feynman once said, "To those who do not know mathematics, it is difficult to get across a real feeling as to the beauty, the deepest beauty of nature." He wasn't being an elitist, he was expressing a genuine sadness. It's like trying to explain the beauty of a symphony to someone who can't hear. You can describe the loudness and the rhythm, but they are missing the harmony. But the good news is the harmony is there. It's there in the way the light hits a soap bubble. It's there in the way a ball bounces. It's there in the very atoms of your body. The universe isn't just described by math. It is a mathematical masterpiece that we are slowly, painfully, and gloriously learning to read. And the best part, the book is still open. There are chapters we haven't even glimpsed. There are symmetries we haven't named and constants we haven't measured. But as long as we keep following the math, as long as we trust the language of the universe over our own limited common sense, we will keep moving forward. Because in the end, that's what physics is. It's not the study of things. It's the study of the rules that make things possible, and those rules, they aren't written in stone. They are written in the most beautiful, terrifying, and perfect language ever discovered. So next time you see a simple equation, don't just see a tool, see a window, look through it. Because on the other side isn't just numbers, it's the very soul of the reality we inhabit, and the avalanche is just getting started.